For problem 1, we're asked to find the thickness of insulation on top of a copper plate that has water flowing on it, such that the insulation reduces the total heat loss from the plate by 90%. The learning objectives are conduction, convection, resistance networks, and then Cartesian coordinate systems. And in this problem, we know the temperature of the plate, the K for the plate and the insulation, the velocity and the plate length, and we have to find the insulation thickness. We can assume 1D heat transfer, that at steady state, that K and H are constant, and the average temperature is 40 degrees Celsius. And using that average temperature in table A9, we can find the properties of water. Next, there's several steps that go into finding the H for water, and those include finding the Reynolds number and the Newsett number. And then once those things are known, we can find the H, which is 5,283 watts per meter squared Kelvin. Next, a heat resistance network is set up for the system with no insulation, which only includes conductive and convective heat transfer, and those can be used to find the total R, which can then be used to find the total heat loss from the system. And the heat flux from the system when there's no insulation is negative 91,057. Then, looking at the heat resistance network with the insulation, there's 2 different conductive heat transfers and 1 convective, which can find the following R total, where the only unknown is L2. Then, knowing that we want to reduce the heat loss by 90%, the new heat flux is determined to be negative 9,106. And if we plug that into this equation that we used above, we can determine the thickness of the insulation to reduce the heat loss by 90% to be 0.277 millimeters. In the next problem, we have a potato that is covered in foil, and we are asked to find the temperature at the interface between the potato and the foil. And learning objectives are deriving the conduction equation, solving the conduction equation, and then spherical coordinate systems. We know the radius, we know the temperature at a known radius, and then we know the temperature at the foil surface. And we want to find the temperature at the interface between the foil and the potato. And we can assume at steady state that it's 1D heat flow and there's no heat generation and the constant K and H. Using this information in table A7, we can find values for properties for potatoes. And looking at the heat conduction equation and the following simplifications, that there's constant K, it's 1D heat flow, there's no heat generation in steady state, we can derive the following form of the heat conductive equation. Then, with the 2 known boundary conditions of what R is and its known temperature, as well as the interface, we know that the 2 different types of convective heat flux can be set equal to each other. We can solve for C1 and C2 in the temperature profile, and we can find the full temperature profile of shown below. Then using that and plugging in the R of interest, we can find the temperature, which is 30.62 degrees Celsius.